So good morning again, class. Thank you for the people who are coming online. As I said, I will record this lecture. So for you, you can review this lecture on video if it's not very clear doing this on the Zoom. Or some other people can get on and retrieve the video and review that at a time of your like. So because I'm currently out of town at a conference, so I wanted to make sure that the class is continuous as scheduled. Before we begin, please make sure your microphones are muted to minimize the background noise. If you have any questions during the lecture, feel free to use the chat function or the raise hand function.
Lecture or in lecture.
So I will address.
Bro, you took my speed. Bro, you took that speed. How did I take your speed? That's not even my stuff.
Could anyone please mute your microphone so we can minimize the background noise? Thank you.
Yeah. Is
Let me do that. Okay. So let's. I'm looking forward to getting engaging and have a productive weeks for this lecture. We have finished the midterm exam last week. I haven't get a chance to grade it yet. I asked my TA Akram to do some with the multiple choices questions. So I hope I can get this ready by next week. Okay, before I start, I want to get into MATLAB examples, and then we will dive into today's topic. If there are any questions here, or even with the grading of the midterm exam 1, if you have any questions before we start, please raise your hand. Okay. So let me share this. Sharing. Okay. So here is a MATLAB example. We did it part of that last time. Let's look at it, how to use that to very easily to draw the poles and the zeros for a rational function. So as we know, for Z transform, these are very important for us to analyze the system. So first we did that. This is x1, x2. We did a convolution. We did a deconvolution. So we have some functions b and a. B's are the polynomials, b0, b1, b2. These are the polynomial coefficients of the numerator polynomial. A's are the parameters of the denominator polynomial of my rational function. So we did that. Now let's look at after that from line 20. I have b equal to 1. A is equal to polynomial of 3 poles. Actually, those are the 3 roots, 0.9, 0.9, and a minus 0.9. Therefore, I know for my polynomial on the denominator, it's just b0 equal to 1. That's just 1, right? 1. And then on the numerator, on the denominator below that is a polynomial with coefficient of a. But here I have all these roots, which are the poles. So I know I have exactly 3 poles at 0.9, 0.9, minus 0.9. And of course, I can calculate the residual doing the long division of b and a. I don't have any, I only have a proper rational function. So, right? So here on the Z plane, I'm going to plot this out with the polynomial b and a. So I pause that. Let's look at what we have. This is doing a deconvolution. Okay, so here we go. So can you see that? Maybe I should. Let me share the entire screen. Entire screen. Okay. Can you see the picture? Figure. See the entire. Okay. Great. So this is what we have, right? That's a Z-plane. Well, we do have 3 poles, 2 double pole at 0.9, 1 pole at minus 0.9, and we do have 3 zeros, exactly the same number as poles. So 3 zeros are deformed onto the origin. So it's right here, set 3. So that's what we expected. All right, so let's look forward. Now, I have a B is 1, 0. B is 1, 0 is the same as B is equal to 1, right? So that's B0 equal to 1. B1 equal to 0. That's nothing. So on the numerator, I still have a 1. On the denominator, I have A0 is 1. A1 is minus 0.9. So what I have here is, let's see if I can do this. There. So I have 1 on the numerator. Denominator is 1, subtract 0, 0.9 c to the power minus 1. Okay, so that's the polynomial 1 and 0.9. Therefore, I do have 1 pole at 0.9. That should be the result. So I'm going to plot this out. Let me do that. So we don't care about the frequency yet. Let's just look at the Z-plane. So here is a Z-plane. I have 1 pole, 0.9, from the polynomial, and I do have 1, 0 on the origin. So that's what I expected. So let's look at the next example after that. Now, after this stop, I have a B is equal to, that's an array, 1, 0, 0, 0, 0, 1, minus 1. So what we have is B0 equal to 1. Here is actually B sub 8 is minus 1. A is 1. So on the numerator, we have this polynomial. On the denominator, that's just 1. So we don't have a denominator. So in terms of the polynomial, I have something like this. Turn this up. So the second example is I don't have a denominator, but on the numerator, I have B0 is 1. Subtract, well, it's minus 1, right? So it's minus 1 at the z to the power minus 8. So it's actually B sub 8 is minus 1. B sub 0 is 1. Okay, so this is my polynomial on my Z transform. Now, for this guy, what are the zeros of this function? Which is what are the roots? This is equal to 0. What are the roots? How many zeros, how many roots do I have? Well, we know this is 1 subtract z to the power minus 8 should be equal to 0. Calculate this. And then what's the solution? Well, z to the power of 8 is equal to 1. Z can be a complex number. Therefore, z can be equal to 1 minus 1, j minus j. What else? Actually, 45 degrees, right? It's actually on a z. Oops, a little bit here. So if you have this is unit circle. So I get a 1 minus 1 is a 0. It's a pole here. J minus j. I have another 4 at 45 degrees. So it's here, 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 and here. Basically, you have a more 1. The angle is 0, 45 degrees, 90 degrees, 135, 180, and so on and so forth. So I do have 8 different poles. But in this case, I'm sorry, it's zeros. That's on the numerator. So the zeros at those 8 locations. So let's look at my example here. So continue with that. And I don't care about the frequency. I want this. So this is the pole 0 plot. Indeed, I have 8 zeros along this unit circle because more is equal to 1. So those are 8 zeros. And then I have 8 poles, equal amount of poles exactly on the origin. Okay, so the last example here is I am changing the order of A and B. B is equal to 1. Therefore, B is 0, B not equal to 1. Numerator is just 1. There are zeros, but zeros are deformed onto the origin. And the denominator, I have a polynomial. A naught is equal to 1, and A sub 8 is equal to minus 0, minus 0.9. I want to make sure it's a little bit shrinked inside the unit circle. I want to make sure my system is stable. So in this case, if I get down to my board here, oops, what I have on the denominator is this is 1 subtract 0.9. Excuse me, on the denominator, c to the power minus 8. Right. On the numerator, it's just 1. So this is the third example. And then I calculate the poles. Make sure this part is equal to 0. And you can also calculate 8 different poles. They are equally along the circle. So let me run this to the end. So here is indeed what I have. These are 8 poles, a little short of 1, but they are along these 8 equally spaced faces. And then I have 8 zeros on the origin. So that's the 0 pole plot. Okay. Great. Are there any questions on these? All right. Next time I will show you a Z-transform symbolic MATLAB code. Actually, it's very nice. You can do a forward and the inverse Z-transform in MATLAB. We will see that in next time. So let me get to today's lecture here. Here. Okay, so let me start it from here. See how I can do that. Get this. All right, can you see the screen? Okay, wonderful. So here, let me do this. Yeah. Great. So here is I'm doing inversion of Z transform. And we know mathematically, I need to do a contour integration with the variable in the complex Z domain, which is a little involved, and I don't want to do that. We have some of the methods in DSP, we can do that in a much easier way. So instead of doing contour integration, I can write this in a power series expansion using long division. Now, if my polynomial is improper, so I can do a long division. And the first part we said last time is very easy. Right? It's a polynomial. You can actually do that inverse transform by observation. We will see an example. And then the rest is the remainder, which is a proper rational function. Then we need to dig into today, do a partial fraction expansion of that. So if xz is rational function, so I have bz over az. B is a polynomial with coefficient b's. A is a polynomial with coefficient a's. If this rational function is proper, that is the order m will be strictly less than the order of n. So I will not be able to further do the long division. Of course, I need to make sure that a sub n is not equal to 0. So this I do have this n right here. Okay. On the other hand, if I have an improper rational function, which means these orders m are greater than or equal to n, then we can always do a long division, make it this part, and then the rest is my remainder, which is a proper rational function. So we said doing inverse Z transform, inverse Z transform of this polynomial, Can we do that? We did it before, right? Weeks ago that we actually can do that relatively easily. Z transform, inverse Z transform, linear operation. So I can do a Z transform on C naught, which is, well, C naught, and then I have a delta N if I'm doing inverse Z transform. Second term is C1 and the delta C minus 1 is just a delay. So N minus 1. Okay, that's it. And then I can do the rest. So this part, the polynomial part, is very simple. So now let's focus on this proper rational function. So let xz be a proper rational function written in this format. So if it's proper rational function, I do have this condition. N is strictly greater than n. You can do all the polynomial as a function of c to the minus 1. Okay, mathematically, we can do that. If we are not very comfortable with polynomial c to the minus power, you can change that, as in the book, change to z to the positive power. So the rest is kind of following the textbook. So I multiply both sides by c to the power capital N. This is the numerator, and the denominator times c to the power N. So I get this term, right here. And then if you look at that, well, z to the power n, it's not a proper rational function again. So I can do this. A little trick is I divide this entire xz by z. So I just make sure that polynomial on the numerator has the largest order is n minus 1. So again, it's a proper. So this thing in the box, that's proper. I just do a little trick. If I have a proper rational function, then what I can do, I can divide that into components, different components adding together. Suppose I have distinct poles. Now, let me flip back to the last page. Poles is the root of this numerator, the denominator polynomial. Well, how many poles I have? How many poles I have? How many roots I have for this polynomial, which is n roots or n poles, right? So suppose all these n poles or n roots are different. We call that distinct n poles. Then I can always decompose this term, proper rational function, into these elements adding together. Each one of those is a proper rational function. It's proper. So this is proper. The next is proper. Everything is proper because the entire thing is proper rational. It's a proper rational function. So if you look at the first term, it's a1 over c subtract p1. In order for this to be proper rational function, the denominator I have poles, one pole, so its order is 1. The numerator should have order strictly less than the order of denominator. Therefore, the order of numerator has to be 0, right? 0 meaning that I don't have z's in it. It's just constant a1. Very nice. So it's a1 is constant, a2 is constant, and an is constant. And we want to determine these constant coefficients, a1 through an. How to do that? Well, follow the book. We have this. Well, there are many ways to do it, but I think this is an interesting way. So let me still put this is my box. xz subtract z. So I multiplied both sides by z subtract p sub k. Z subtract p sub k, z subtract on both sides, left and the right. So if I multiply this on the right, because all these poles are distinct, so pk and the p1, they're different. So the first term, I have to leave it here. The only thing that cancel out is when I am dealing with the kth term, because you have a z subtract p sub k on the numerator, z subtract p sub k on the denominator. So cancel out. I have just one constant. And then all the way to the last one, because this and this are distinct, so you keep it there. And then we can do that. I plug in z equal to p sub k, one particular value, right? That's just one pole. You calculate that pole, p sub k. You plug into this equation. Actually, you plug into on the left, plug into here. On the right, you will see the effect because z equal to p sub k. So this is 0. This is 0. Everything is gone except this middle term is a constant, a sub k. That's what's left. Therefore, a sub k is equal to, this is the entire thing on the left when you plug in z equal to p sub k. Okay. Similarly, I can do for a sub 1, a sub 2, all the way to a sub n. In addition, because I know if I have real coefficients, a's and b's, my poles are complex conjugate pairs. So since P2 is equal to conjugate of P1, and therefore we can actually prove that A2 is complex conjugate of A1. So you don't have to do that. You can reduce your calculations by half. So that's how we calculate distinct poles. Are there any questions? Slow down a little bit. All right, let's go. If I have multiple order poles, I have p sub k happen twice, 3 times, m times, okay? If xz has a pole of multiplicity of m, that is, it contains its denominator, the factor of z subtract p sub k, but to the power m, then what we need to do is the partial fraction expansion must contain these terms. I will have m different terms. The denominator is this to the power 1, to the power 2, all the way to the power n. I have all these terms, right? Therefore, how to calculate this constant coefficient, a sub 1k, a sub 2k, a sub mk? Well, what we can do is I can multiply my equation, both sides, left and right, of my previous page, with c subtract p sub k to the power m minus 1. Excuse me, to the power m. And then I plug in z equal to p sub k. Therefore, all the other terms are canceled out, right? Because you do have p sub k. Only the last term here, you got z subtract p sub k raised to the power m, and you have this term. These two will cancel out. And what you left is exactly a sub mk. That's the constant coefficient here. How to do with the other a's, a sub k's? Well, we need to do a little bit calculations. So I take this term, which is the entire term. Entire term with what I meant is xz over z, right? This entire term. You multiply by z subtract p sub k raised to the power m. And then I do a differentiation. First of all, differentiation with respect to z. And then I plug in z to p sub k. What you get is the coefficient here, which is somewhere here. Second to the last, which is somewhere here. That's a sub n minus 1k. And then you do, with the entire thing, you do a second derivative on z, all the way to the n minus 1th derivative on z, plug in z equal to p sub k, and you find the first coefficient, which is right here. Okay. So that is a way we are dealing with multiple order poles. And later we will show some numerical examples and to see how this method can work. All right, so that's good. So after that, if I can successfully calculate all these a's for my partial fraction expansion, so now I remember I still have this, right? I still have a kind of a xz divided by z, because I want to make sure my polynomial is function of z instead of function of z to the minus 1. So it just conventionally, it's easy for me to find all the roots. And then I find this partial fraction expansion. Suppose I have all these p distinct poles, and then what I have is this term with all the a's are none. Then what I can do is I multiply this equation left and right by z. So this z will cancel out. So what I have here is xz. On the right, if you multiply a z here, multiply a z here, and then the denominator becomes 1 subtract p sub 1 z to the power minus 1. And then the second term is denominator 1 subtract p2 z to the power minus 1. So this is very nice. That's what we are familiar with. We just have 1 subtract pole raised to the times p to the minus 1. Right? And then I can easily do a z transform on this term. Well, remember, a1 is something I know. I know it's a constant. And then the z inverse z transform on this part, it's easily we can look up the table, or we already know that because pole is the root of my difference equation, right? So I do have a pole here, which is p sub k. They are put as the root. So p sub k to the power n in the time domain solution, right? P sub k to the power n. The only part here need to be careful is this system causal or anti-causal? If it's causal, as we show that on the exam, if it's causal, that the region convergence is the exterior of a circle. It's greater than something, greater than absolute value of this pole. Causal, so I simply put this root raised to the power n times un, meaning that this is a causal function. If it's anti-causal, then I have a region of convergence, which is interior of this circle. It's a disk. And then you have this root multiplied by anti-causal unit step function, which is minus. Don't forget this minus u minus n minus 1. Right? So this is easily done doing this inverse transform. So that's for this. And the same thing for the second term, you pull out a2, and then you have a pole p2, root is p2. And then the last term was an over that. So we can do everything. So each individual term, I can easily do inverse Z transform. That's how we do a partial fraction expansion, right? We divide and conquer doing the inverse Z transform. In case of a double pole, let's just look at the first one. In case of double pole, which is Z subtract P squared. Same thing, I multiply both sides by Z here, both sides by Z here. So on the left, I have a very clean xz. On the right, I'll have this. Again, this is z minus 1 in the square term. I have another z minus 1 left on the numerator. And that's also from the lookup table. It's very easy to find. So this is indeed from lookup table. That is my pole, which is p raised to the power n. But you have a time variable n here. How wonderful. This is what we know from the difference equation, right? Difference equation, if I have a double pole or double root, and I do have this term here, and just to make sure that it is independent of another term, which is p to the n. The same thing here. So similar discussion, if it's causal, and then I put a un here. If it's anti-causal, so I put a minus u minus n minus 1 here. So I can do that easily by lookup table. Now, I have those dealing with a single pole, double pole. What about if I have multiple poles, like raised to the power 3 or 4? Well, as we said before, right? If I want to, because my coefficient of my polynomial a's, which is denominator, these a's, a0, a1, all the way to an, because all these a's are real numbers. Therefore, the polynomial, the poles are conjugate pairs. So you can doing a raised to square, and if you have a third cube, you can easily decompose again into the order of 1 or 2. So there's no higher order. I can always decompose that. Okay. So it's actually showing here on this slides. So if everything is real, meaning that my polynomial b's are real, a's are real, Usually that's the case for a practical system. Then I can always decompose that, into these poles, these zeros. And then let's say doing a long division. Suppose it's improper rational function in general. So doing a long division, this is the first time. It's this part doing a Z inverse transform easy by observation. The second term here is that I have a single real pole, and then I can put all these in this simpler format. Easy to do that inverse D transform. The third term here, I have two poles, but these poles, they have to be complex conjugate of each other because I need to make sure all these coefficients are real, right? This is alpha, by the way. It's not A, it's alpha 1 sub k, alpha 2 sub 2k, alpha 1 and alpha 2, they are complex conjugate of each other there. So I can always do with a polynomial on the denominator, the highest is 2 for all real coefficients, right? So that's why when I said for the denominator, the second order is the highest I can get. If you have third order, you can always decompose that. Make sure everything is real. So if you're doing this on this page, everything, these coefficients are real. Alpha, beta, and then gamma here. And then of course, these if you want to find out these poles and the zeros, all these are real. Okay, so this is the partial fraction expansion for doing an inverse E transform. Next time I'll give you some examples. I'll see if I can get a pen, can write on my canvas, so it's easy for me to show you some numerical examples. Are there any questions so far on this part? All right, it's good. If you have questions, put in the chat or simply raise your hand or send me an email. I'll answer afterwards. So with these, let's look at LTI system in the Z domain. So now I know I can do a forward Z transform. Once I sort out everything in the Z domain, I'm ready. I can always do an inverse Z transform, get back to the time domain. So Z transform is really a very powerful tool for me to analyze LTI systems. Let's look at some more details. If I have a zero pole system represented by the linear constant coefficient difference equation with arbitrary initial conditions. So linear constant coefficient difference equations, we have coefficient A's, right? Coefficient B's. These are the coefficient of my difference equation. Now, in the difference equation, what are the coefficients of A's? These are the coefficient of my feedback loops. Coefficient of B's, these are the coefficient of my feed-forward loops. So this is dealing with Xn. Of course, you will have some of the delay, Xn minus 1, Xn minus 2. A's are dealing with Yn, right? That's feedback. So you have Yn minus 1, Yn minus 2, so on and so forth, okay? So in the rational format, this is a polynomial on the numerator with coefficient B's. And then I have a polynomial on the denominator with polynomial A's. So this is my rational function in the Z domain corresponding to the difference constant coefficient difference equation. Okay. Assume that I have an input signal Xn also has a rational Z transform, which is capital XZ, rational Z transform. So I can put into a numerical term, numerator polynomial, denominator polynomial. If the system is initially relaxed, now we test this on the exam as well, right? So initially relaxed, that means at time, suppose my time is 0. My N naught is 0. So you have N naught subtract 1, N naught subtract 2. So we have initial condition is Yn minus 1, Yn minus 2, all the way to the highest order of my system, Yn minus n. everything is equal to 0, so it's initially relaxed. And then the output in Z transform, it's very easy in the Z domain. That's simply my system response times the Z transform of the input. So I have this B over A times Q over N over Q. And I give you, that's my output, YZ. And what is the solution for that? Well, you go ahead and do an inverse Z transform. You will find out, right? So it's very easy. Suppose the system contains simple poles. Simple poles meaning that's distinct poles. P1, P2, all the way to Pn. These are the poles of AC, right? That's the poles of my system, of AC here. So this is the poles of the system. And then the Z transform of the input signal contains poles Q1, Q2, all the way to QL, where these P poles, Q poles, they are not equal. Everything is distinct. So those Qs are the roots of this polynomial, QZ, which is here, QZ. So that's we call that a pose as well, the pose of my input signal X. In addition, suppose there is no zero pole cancellation. We will see cancellation in the last page. So if there's no cancellation, so I have to leave all these poles here on the table. A partial fraction expansion of YZ, well, now we know that, right? It's easy to do. It's simple pole, distinct pole. Therefore, partial fraction expansion, this is for the system. So we have this. This is for the signal. We have this. So on the denominator, it just a single Z to the power -1. So we have one pole here, another pole here. On the numerator, these are the constants, even though I need to calculate these constants when I do the partial fraction expansion. And then I can do an inverse transform of YZ. Now I can do inverse transform. So easily for me to find out Z transform, a Z domain Y, then doing an inverse Z transform, get this. Yn equal to this part, we have pole, so that becomes a root here. A sub k is constant, so it's constant. And suppose it's causal, system is causal, so I put a un here. Similarly, I have a pole here, which is q sub k, becomes my root. And the constant q's, it's just constant putting here. And then it's causal signal, so un. So I'm done, right? It's easy. I can find out the inverse transform of YZ, which is the output of my system. The first part is called the natural response of the system. Natural response, we have mentioned this before. Natural response, everything is caused by your system. This is because your feedback. This is new denominator is really about the feedback. So you have some feedback. It's going on forever. We call that the natural response of the system. Second part is the forced response. Forced by the input. So this is really caused by those cues. This is from the input signal, so it's forced. Let's look at these two parts separately. The first one is the natural response of the system. If P sub k absolute value is less than 1 for all k, then because it's raised to the power n, excuse me. And it raised to the power n. When n increases, starting from 0, when n increases approaching infinity, then eventually this part will be decaying to 0 because P sub k is less than 1. And therefore, this natural response, which is feedback, eventually it will die out. It will die out. The system is not going to evolve forever. Otherwise, you will have an unstable system. This is my stable system. And this process is called a transient response. So you have something over time, the system feedback will die out. It's called a transient response. I have an example before, right? When you do the circuit board, you have an oscillator of AC. with a frequency, low frequency, let's say 100 hertz, and you suddenly give a 300 hertz or different voltage, your AC circuit is not going to change suddenly, right? If those capacitor resistors, it's going to do this transition period. Eventually, the effect of that will die out and it will follow your new signal. So this is transition response is caused by the natural response. The second part is the forced response. Forced response is following your input signal. So input signal itself better not to be unstable, right? Otherwise, as the time goes on, your signal becomes larger and larger. It's impractical. So it has to be some stable signal. And the signal will not die out. Otherwise, there's nothing to discuss after a while. So the signal is usually it's oscillating. It's a periodic signal. That means these poles are fall on the unit circle, which means that these QK's absolute value is equal to 1. And therefore, you will have an oscillation all the time. It's not going to die out as n increases. It's not going to be infinitely large. The forced response persists for all n greater than 0 because it basically it just oscillates. The forced response is called a steady state response of the system. As I explained, if you have a circuit board, that oscillation now changed to a new frequency, 300 hertz, instead of original 100 hertz. So, but you follow that steady state. The transient response kind of die out, and then you have the new one. So this is very nicely explains something from the DSP perspective, why we are having some, you're doing hardware or software, you will have the transient response time, and what's when you reach the steady state response. Okay. So the last part for today is I like to use this the system function to discuss the causality and stability in this case. We also mentioned this before. So today, let's from the Z domain get into some good mathematical background. First is a causal linear time invariant system. Causal system in the time domain, we can look at the impulse response, Hn. Simply, this is the condition for causal system. Hn equal to 0 when n is less than 0. We also know that region of convergence of a Z transform of a causal sequence is the exterior of a circle. So the region of convergence is the outside. Is the outside. Okay. So an LTI system is causal if and only if RC of the system function is the exterior of a circle. For radius R is finite, and then because exterior, including the point Z equals to infinity. Then we look at the stability. For a BI-BO stable system, in a time domain, we can also have this condition on my impulse response. So the impulse response should be absolutely summable. And then I bring everything to the Z domain. So HZ is this, right? This is my Z transform definition polynomial. And then I check with absolute value of HZ, absolute value, because I want to make sure this entire thing is stable. It's in the region of convergence. So I put in a absolute value here, then you put in the absolute value inside the summation, so you have a less than equal to this. And then you make these two, and you have equal sign. Now we have did that before. So the next part, this one is the trick part. When I evaluate the Z transform on the unit circle, which means Z absolute value equal to 1. Now, so this is my Z plane. This is my Z plane. I'm not going to get all the complex variable Z. I only need to concentrate on the unit circle. Sorry for this circle. So this is with mode 1. So Z absolute value equal to 1. So I'm only going to check all these Z's on the unit circle. As later we will know, that's a special case for Fourier transform because we only look at frequency or the phase. We don't really look at the mode or the amplitude of C. If I'm doing this, the last term, this part will goes away, right? This part will become 1 because you have absolute value of C equal to 1. Therefore, I have absolute value of HZ will be less than this, less than infinity. So if my system is BIBO stable, that means the region of convergence includes the unit circle, right? Is this logic satisfied? Well, if I have a BIBO system, this is true. This is true. And then I check my Z transform of HZ. I want to check with the region, unit circle. Unit circle plugin is this. You just tell me this is less than the infinity. Therefore, the unit circle is indeed in the region of convergence. From this, it's a finite. So it is indeed, it is finite. When I check this, it's go. So the region of convergence includes the unit circle. Which, by the way, makes sense, right? Because unit circle, as I said, is the Fourier transform. You're looking at the frequency. So if I want to make sure this system is really implementable, so for different frequencies, the unit circle should be converged. Z transform, should be able to do that. In other words, you should be able to do a Fourier transform on that, which is Z transform evaluate on a unit circle. Okay, so combine these two together. Last 2 minutes. Combine these two together. Causality and stability. If I have a causal system and a stable system, so usually a practical system is both causal and stable, they must have a system function converges for Z greater than Z absolute value greater than R, where R is less than 1. So we have, first of all, the system converge for that. This is for causality. It's exterior of a circle. So let me draw this again. So for causal system, the region of convergence should be outside the circle. Now let's say the circle is R. The radius of the circle, this is R. This is R here. This R should be strictly less than 1. The reason is that because my unit circle, as I said, the unit circle should be in the region of convergence. Unit circle that has to be in the region of convergence. Therefore, this R should be strictly less than 1. Unit circle is 1. Right? So combine these two together, we have a statement that a causal LTI system is BIBO stable if and only if all the poles of HZ are inside the unit circle. Well, let me change another color. So here is a pole here, a real pole, another pole here, complex conjugate. This is okay because the poles are not in the region of convergence. So they are inside the circle. And I just said this R should be less than 1. Therefore, all these poles, the absolute value of those poles should be less than or equal to R, should be strictly less than 1. So indeed, these poles are inside the unit circle. And that is how we determine if I have a practical system, it is also stable. So lastly, let's just compare this with before you have in the signal system, we are dealing with a rational transfer function of HS in the Laplace domain. You still remember the if and only if condition for the system to be stable? It is that we have a S-plane, it's a complex plane, but all the poles should be in the left half of this Laplace plane, Laplace S-plane. And at that time, my system, this is continuous system, is stable. So you can think of this imaginary axis, almost you bend it, and you circle around. And then you have the Z transform. Z transform is something that inside the circle, all these poles, then I have a stable system. Okay, that's all I have for today. I think it's good timing. Are there any questions so far on these? Okay. All right. If you don't have any questions, I'll conclude for today's lecture. And this will be recorded. I will post it on Canvas when I get a time. So please review the video. And thank you for whoever's coming here online. And I will see you all on Wednesday. Bye bye.
Thank you.
Thank you. Bye bye.